and whoever puts an icebreaker in the chat first, I'll go ahead and use that one. Hmm. Sometimes coming up with these things is hard. Oh, favorite ice cream flavor. Okay, cool, cool, cool. This is a good one. Let's do this. Okay, Aradia says favorite. I feel like I always start off with green. So let's start off with pink today. Yeah, let's start off with pink. Okay. Hello. Oh, I guess I'm like incredibly zoomed out. Okay, there we go. This should be better. Favorite ice cream. I don't know if we've already done this. Maybe I've done it in like another session, but okay, I think this is a good one. All right. For today, our icebreaker. Oh, did we already do this? Just kidding, you guys. We are not gonna do this. Okay, I lied. Favorite moment from Amari. Ooh, I feel like that one's kind of generic. Maybe we can narrow that down. Favorite moment about what? Maybe like, I don't know. Favorite memory? Favorite memory? Oh, wait, wait. Actually, I like favorite memory. Let's do favorite memory. What is y'all's favorite memory? I mean, yeah, actually, no, you guys probably have lots of memories. Okay, and then Cypher says favorite sport. I will keep that in mind for next week. We will do that next week or maybe in tomorrow's class or Wednesday's class. Okay, favorite memory. This one's really sweet. Okay, let's see. What is your guys' like favorite thing, favorite memory? This one's like, I feel like you guys got to think about this a little bit. What do we think? I'd say one of my favorite memories is, oh wait, before I say mine, Tommy says when my little brother was born. Oh, that's so sweet. Okay, little brother is born. That's awesome. I would say, oh, what is mine? I guess like it's like doing like an annual Labor Day picnic with my family. Or not Labor Day, but like annual back to school picnic. Wait, I can't spell. Spelling is hard. Awesome. Okay, let's see what else we have. Oh, Rohan says when my little sister is born. Aw, that's awesome. Okay, cool, cool, cool. Jason says to be born. His favorite memory is being alive. I think that's awesome. You can't have any memories if you're not alive. Okay, Cypernita says my favorite memory is learning about Ronaldo. Ooh, okay. Learning about Ronaldo. Okay, awesome. He is the goat. That's great. Or this is what my little sister is born. Amazing. Amari says, when I found out that I'm getting the Switch 2 on Christmas. Oh, yay, that's awesome. Okay, getting this. So is your birthday near Christmas, Amari? Because I saw you did Christmas slash birthday. Switch 2. Okay, awesome. Let's see what everyone else says. 2 months away. Okay, cool, cool, cool. So kind of just merge them together. That's awesome. And Mika also says what little brother being born. There are more people than I anticipated saying that their happiest moment is when their sibling was born. I'm gonna be honest, that is not what I was expecting. This is really interesting, you guys. Okay. Um, yeah. Oh, even Aditya says little brother being born. Wow, wow, wow. This is awesome. Okay. Wow, you guys are so wholesome. This is great. Okay, let's go ahead and talk about our stuff for today. So I feel like last week we did a good intro into like the world of like shapes. So today we're gonna kind of build on that discussion and we're gonna talk specifically about like polygons and then maybe goes it into a little bit of triangles. But the big focus today is polygons and specifically angles. So let's go ahead and get started with that. Okay, can anyone define a polygon, like to begin with? What is a polygon? What do you guys think? Okay, Hithart says a shape. Okay, but what is a shape? Like what exactly is a shape? What does a shape mean? Okay, Ratika says a closed shape. Okay, I like this. I like this a little more. But still, is that specific enough? I think we can get more specific. Okay, I see closed figure, closed shape. Closed shape. I like this part, but I think we need to get a little more specific. Um, and Vika says a closed figure with three or more straight sides. Okay, I like this. I like this straight sides edition with three plus straight sides. And yeah, what do you guys think about this definition? Is there anything else we can add maybe, or do you guys think this is like a sufficient definition? Do you think this is like a good enough definition? Oh, Jason says a closed figure with three or more straight sides and closed. Okay, yeah. Okay, I think there is some agreement there. Sean also says no round edges. Yeah, I totally agree with that. Um, yeah, okay, cool. So I think we're all on board with this more specific idea. And this is absolutely correct. So a polygon is basically a closed two-dimensional shape, meaning it's like flat. It has no like height or anything, it's flat. And it's got some straight sides. So some pretty common examples include triangles, quadrilaterals, pentagons. Like you guys know all this. This is like baby stuff, right? We know what some polygons are. So today what we're going to do is not baby stuff. We're going to look at two really important types of angles. So I know last week we kind of started this discussion of angles, is particularly in triangles, but today we're really going to expand on that by looking at interior angles and exterior angles. So if you're not aware of what those terms mean, totally okay. We're going to define that today. So actually, let's go ahead and just like jump straight into it. So you know this is what a polygon is, right? So let's go ahead and maybe take a crack at figuring out what an interior angle is. Does anyone know what an interior angle is? Just to start us off. Nope. Okay. That's okay. We can always start on a clean slate. Okay, Anvika says an angle inside a polygon. Yeah. Okay, I totally agree with this. So, how many of you guys know what the word interior means? Like, how many of you guys have maybe heard your parents say like interior design or like interior of the building? How many of you guys have heard that kind of thing? Okay, so yeah, so some people have heard of it. So when I say the word interior angle, you can kind of infer, like based on your context clues, right? You know, like interior means inside. Like this is stuff that you've kind of heard around a little bit. So interior means inside. So if I say interior angle, I'm looking at the inside angle of a polygon. So this is like pretty intuitive. If you know what interior means, like you get the rest of this, right? So pretty intuitive. Um, and basically like we're looking at every like vertex at every corner. So let's say I have like a cute little like quadrilateral over here. That's like a bad quadrilateral. It's got a round edge. Okay. Okay, so this is my little quadrilateral. These are going to be my interior angles, right? Because they're inside my shape. They're inside my polygon. Okay. Um, so something we're going to find out a little later today is that the sum of the interior angles really depends on the number of sides. So do you guys remember what the sum of the interior angles for a triangle is? What is the sum of all the interior angles? Yeah, it's 180. Okay, perfect. And even though we haven't talked about this already, I'm sure you guys have already seen this. How many, or what is the sum of all the angles in a square? Or like any quadrilateral, right? It doesn't even have to be a square because you can mush the square in any shape, any way, and you'll still get 360 degrees. I'm gonna assume that 0 degrees that Aditya put in was a typo. Yeah, it's 360. It doesn't even have to be a square. It could be this thing over here. That's still 360. Okay. Can you guys maybe like hedge a guess? What do you think it's like for a pentagon? Let's draw a wacky pentagon. It's not. I don't want that wacky. Okay. Okay, awesome. So think, okay, Anvika says 125. Okay, think about this, right? If we add an extra side and the number of angles go up, or the sum of the angles go up, I feel like we should be going up for our angles, right? Not going down. Yeah, okay. Cool. So it seems like some people are saying 540, which is Correct. Yeah, this is 540. Um, and I think you guys are starting to see a pattern. We'll do one more and then we'll talk about like what the overall pattern is. So, what do you guys think is the sum of the angles in a hexagon? Wait, I don't want it to be concave. Wait, I also don't want it to be regular. I'm really struggling to draw like non-regular shapes today. Okay, yeah, 720. This is absolutely right. Okay, based on like what we've drawn here and like the number of sides, we said that there's some relationship between the sum of all the interior angles and the number of sides. Can you guys maybe take a guess? Like if can we write a formula for the sum of the interior angles? Like based on what we see here. What do you guys think? Yeah, so there's definitely like some 180 stuff going on. Like every time we add a side, we increase by 180, right? So I think like we can represent a little bit of this with multiplication. And I'm gonna really highlight what Viditya said here, because this is absolutely correct. And you know what? Let me just write this in another color because this is so important. Let's do this. Okay, so the sum of interior angles is going to be equal to the number of sides minus 2. So n minus 2 times 180. And if we go ahead and take a look at everything we have here, right? A triangle has three sides. 3 minus 2 is a 1. 1 times 180 is 180 degrees. If you look at this quadrilateral that is totally not a square, 4 minus 2 is going to be 2 times 180, which is 360. And then you can kind of verify these for the other two things as well. So this is like the general formula for finding out the sum of interior angles in a polygon. Um, Now this is important, and we can kind of talk about like where this formula comes from, why it's n minus 2 specifically, but like the rigorous proof is kind of like beyond the scope of this course. We'll talk about like the intuition behind it though. Like I can't give you guys a rigorous proof, unfortunately. Um, okay, yeah, this is like pretty kind of, this is like a little crazy. Like the fact that we can like represent all of this in like the sum of the angles just based on the sides. Okay, so the reason why we have n minus 2 is because when we take any shape can be split up into triangles. This is like a pretty like mind-blowing idea. Like it seems like, oh, this is so simple. Like, yeah, I can feel like I can make anything from triangles. But this is like really, really important, right? And the fact that every shape can be split up into triangles is a big part of a lot of different proofs and a lot of different theorems. This is something that I'm using in like a second year college course, like in a combinatorics college course. The fact that like a polygon can be split up into triangles. So this is like a pretty revolutionary idea, right? And while I cannot give you a proof, unfortunately, that this is true for every single polygon on the planet, we can't say, well, I guess actually, you know what? We can do a very like base level proof. It won't be entirely rigorous, but we'll do like a small proof. This is like a pretty important idea. So let's go ahead and look at a heptagon because we've done some basic shapes. Let's look at a heptagon. And I'm going to make all of this a little smaller. Um, Let me get my, yeah, wait, actually, never mind. Okay, I lied. Okay, let's make this, what have I not used yet? Oh, let's use some red. Okay, we'll draw a heptagon. So that's going to be 7 sides. What is that? 1, 2, 3, 4, 5, 6. Wait, let's do like a crazy angle. Okay, 6, 7. Wait, my shapes are looking too regular these days. Okay, yeah, 7 sides, perfect. So what I'm gonna do to create my triangles is I'm gonna draw, I'm gonna pick this as like my main vertex. Okay, this is gonna be my home base, and I'm gonna call it A1. And then I'm gonna draw triangles to other vertices to make, or I'm gonna draw lines to other vertices to make triangles. Okay, so do you guys see how we split this heptagon up into 7 triangles? What do you guys think? That's like pretty intuitive, right? That's a pretty easy split to do, right? You just draw lines to non-adjacent vertices. Notice that we didn't draw any line to like this vertice over here. That's because they're already connected. They're already connected by a side, so we can't really draw an extra line. But because this vertex, and I'll say this is A2 and this is A3, Because A3 and A1 have something in between, we can actually connect them with another line. So when we do that, we get a triangle, A1, A2, and A3. That makes up a triangle, right? And we kind of just keep doing that for all these other vertices that are not adjacent to A1. Because when they're not adjacent to A1, we can construct a very nice triangle. So I have A4, A5, A6, A7, right? So how many triangles do we see? We see one, two, three, four, five, right? So how are we sure that this is like the maximum amount of triangles? Like how are we sure this is the best way to triangulate or like split this polygon into triangles? Well, we can see this is true because there's only five other vertices to connect A1 to, right? So if we see in this total like heptagon, we see there's total seven vertices, right? Obviously, A1 cannot connect to itself. So it's like one less vertex for it to connect to, or vertex for it to connect to. We also said A1 cannot connect to A2 or A7 because those are right next to it, and that won't make a triangle. So if we delete those two vertices as well, that leaves us with four other vertices to connect to, right? But notice how when we connect to one vertex over here, or this one vertex over here, this creates this one triangle. And then every vertex after that will create a triangle with the vertices next to it. Okay, so in this case, like this A1, A2, A3 triangle, we can kind of think as like a thing to add at the end. And then every triangle after that will be like two pairs that are next to each other, right? So you'll have A1 and then A3, A4. And then you'll have A1, A4, A5. And then you'll have A1, A5, A6. And then you'll have A1, A6, A7. So notice how all these triangles are just made from A1 and then two vertices that are like not connected to A1 but next to each other. And then we'll go ahead and add A1, A2, A3. So this is kind of like a good example of showing like how we can split this polygon into triangles, which is known as triangulate. So I guess this is like basically a good enough proof to show that like all polygons can be split into n minus 2 triangles. Now I said we wouldn't go rigorous, but I feel like this is like a pretty intuitive enough solution that you guys should be able to like understand like, okay, I can split polygons into this many triangles. So because we can split a polygon into some number of triangles, n minus 2 triangles, remember we said that every triangle has a total sum of 180 degrees, right? In their angles. So if I have n minus 2 triangles, and none of the triangles like overlap or anything, they're all different, and each one contributes 180 degrees. That means in this entire polygon, I have n minus 2 triangles. Each one gives me 180 degrees. So that means I have a total of 180 times n minus 2 degrees. Okay, what do we think about that? Is this an idea that makes sense? I think I saw like a hand raise at some point in here. If that person wants to ask their question, you're welcome to raise your hand again, because I don't know who raised their hand. But yeah, this is like a pretty important idea. The idea of like triangulating is like pretty big. So like if this needs to be re-explained, like I'm so happy to do it. Okay, cool. Oh, it was an accident. No worries at all. Okay, so we have some questions. All right, let's take a look. Okay, so the big idea here is we're taking a polygon and we're breaking it down into triangles. Triangles are easiest because they're three sides, so that's like pretty easy to do, right? You can take two sides that are kind of already like on here and then take the other side to be one that's like drawn manually by hand. Okay, so in this case, we take this little heptagon and all we're doing is just drawing a bunch of diagonals, really. We're just drawing some diagonals starting from A1, going to all these other vertices. Notice that A1 to A2 isn't a diagonal. That's a side. So that's why we're not really drawing anything there. But A1 to A3, that's a diagonal because these vertices aren't next to each other. So that means we're connecting two vertices that haven't been connected before. So when we connect all of these, notice how our little polygon gets split up into a different number of triangles. Specifically, there are five triangles. So because there's five triangles and each triangle has 180 degrees inside of it, that means in total, we will get 5 times 180 degrees or 900 degrees in this heptagon. The reason why we can just go ahead and multiply 5 by 180 is because all of these angles in the triangles contribute something to the heptagon. Like none of these triangles overlap, so none of our angles are overcounted, and all of these triangles cover some part of every angle. So that means we're not undercounting either. We're getting exactly the number we want. So that's where this like 900 is coming from, and that's why it's okay to do this triangulating method. Okay, hopefully that clarified it. If you guys have more questions, feel free to stick around after class and we can kind of talk about this a little more. Okay, cool. So whoever said, Cyberneath, yes, you are right. This heptagon has 900 degrees. Okay, awesome. Um, cool. Let's see, what else? All right, so I guess this is like a pretty good discussion of interior angles. Let's go to exterior angles. So I'm gonna go ahead and kind of, I feel like we know what a polygon is now, so I'm gonna kind of put this definition away and let's clean up this so that we can introduce exterior angles. Okay, so based on what we've talked about and based on like how we've kind of wrapped our head around interior angles, what do you guys think exterior angles are? What are exterior angles? Okay, yeah, they're outside angles. Yeah, that's perfect because we know the word exterior means outside, right? So exterior angles are outside angles. For some reason, this looks like a black. So exterior angles are outside the polygon. So that's like, okay, wait, what the heck? How do we have an angle outside the polygon, right? So let's take a look and let me see what you guys think. Like, let's see if we can figure out this exterior angle outside the polygon. Okay, we'll keep it simple. I'll keep it regular this time. I'll draw you guys a regular pentagon, a regular pentagon. Wait, okay, hold on. Work in progress. I feel like this is good. Okay, yes, yes. Oh, yes, this is a beautiful pentagon. Okay, perfect. All right, so, is this an exterior angle? What do you guys think? Is that the exterior angle? Because that's outside the polygon, right? Is that exterior? Yes. Okay. It seems like everyone is saying yes. Okay. Actually, this is a trick question. The answer is no. This is not an exterior angle. Okay. Don't feel bad if you said yes. That was totally a trick question. Okay. So for those of you guys that are now saying no, what do you guys think the exterior angle is? What do you think the exterior angle is? If this is not the exterior angle, where could the exterior angle possibly be? Like, where can we find this elusive exterior angle? What do you guys think? Okay, maybe everyone is saying no because I said this is a trick question and the answer is no. Okay, let's think. Okay, so we said that this is not an exterior angle. We can't just look at the thing like right outside of the like of this little angle over here. Cyberneath says, is it in the middle of the points? Do you mean like maybe do you mean like inside here or do you mean like maybe like wait, what do you mean middle of the points? Which points are you talking about, Cyberneath? You may be onto something here. I just may be completely misunderstanding. Okay. We also have another idea from Bichette, which is to extend one side at the vertex. Okay, I think. Oh, on the line. Okay, so actually, if we hold on, let's go back to Cyprene's idea, and then we'll look at Bichette's idea. So if we look kind of at the middle of the line, well, if I just look at this angle, isn't that 180 degrees? Because it's the line, right? So a line has 180 degrees. I think this is like you're like onto something with the line, but I think like Vicious ideas kind of on the right track here. So let's say we go ahead and extend this line, right? So then what's the exterior angle? We have this is an interior. Do we think this is an exterior angle? What do we think about this? Ooh, Amari says that he's seen this in IXL. Okay, yeah. This might have been in IXL. Hopefully, this is more like interesting than IXL. Okay, yeah. This is an exterior angle. Yes, this is absolutely correct. Okay, I see some people are like, oh my gosh, I'm scared. Do not be scared. So let's talk about like why this is not an exterior angle because this is what we call a reflex angle. because it is bigger than 180 degrees, but it's less than a full circle, right? Because of that, we classify it as something different. We'll call this a reflex angle. It's not going to be an entire exterior angle because this is just messy to work with. Working with stuff greater than 180 is like not ideal when we're talking about angles. So in this case, we'll have, this is the exterior angle because notice how if we just draw the rest of this, we get the same reflex angle that's over here. But all we're doing is adding like an extra 180 degrees, which is kind of pointless to us because we don't really care if there is an extra 180 degrees because all the exterior angles will have that. So why not just make it simple and look at the smallest thing that to consider, right? Which is this little thing we get when we extend this line and then draw the angle with one side and the line extended. Okay, yeah, this is not a trick question. This is like actually a legit question. So how do I feel about like this new definition of an exterior angle? Is this like good for you guys? Because this can be tricky. We need to make sure we understand this because exterior angles come up for quite some few properties. Okay, we feel good. This is good. Okay, awesome. Okay, so let's go ahead and explore something super duper cool. If you thought interior angles, that formula we just discussed was neat, okay, this is going to be even more neat. Yeah, this isn't like super difficult, but it's super important. So that's why I want to spend time on it. Okay, let me draw the exterior angles for everything. And let's get rid of this nasty reflex angle. Nobody really likes reflex angles. Okay. Wait, I'm like really proud of my pentagon. This is like a nice pentagon. Okay. Um, cool. So if we draw, oh no, I lost my ore. Okay. So let's look at all these exterior angles. Right? These are all the exterior angles. Can you guys maybe take a guess? What do you guys think the sum of these exterior angles are? Can we say anything about that? Like, do you guys think maybe there's something we can say about these exterior angles? Or like, am I just like completely like confusing you guys? Do you guys maybe see something here? Okay, Shonik says it might be 180. Anvika says it might be 360. Okay, and some people are like, maybe there's nothing at all. Oh, some people say it's 540. Some people say it is, what is 62 times 5? 310. I see. Oh, 72 times 5. Okay, 360. Okay, interesting. Okay, before we confirm like whether or not these are right, maybe we need to step back. Maybe we need to go to a simpler polygon, right? Let's go to some quadrilaterals. I'll be nice and I'll draw a regular quadrilateral, which is just a square. I don't know, is that square? That looks like a square, right? Okay. So then if we look at the exterior angles here, I'm gonna go ahead and extend. You know what? Let me draw this in a different line, like a different color. So it's very clear like what's the exterior angle. Okay. So in this case, my exterior angles would look a little something like right angles. Okay. So what's the sum of these exterior angles? Yeah, all of them are 90 degrees. That's right, separate. But I don't want to focus on that because that's kind of just like a thing because it's a square, right? Because it's a square, the exterior angles are 90 degrees. But what's really interesting is that the sum of all of these is going to be 360 degrees. Now, do you guys think we can say the same about this pentagon? Do you guys think, does this look like it's going to be 360 degrees? Okay, Cypher says no, and it seems like some people are kind of agreeing with him here. It doesn't look like it's going to be 360 degrees. Shonik says yes, Anvika says yes, Arathi says no, Arav says yes, Amari says no. Okay, so we're kind of split here. I'm gonna tie break, and then we're gonna talk about like why what I'm gonna say is true. So it actually turns out for all polygons, for any convex polygon, the sum of the exterior angles is actually 360 degrees. I know that's crazy. Some of you guys are like, there's no way this is going to be equal to 360 degrees in the polygon, but it actually is. So we'll talk about why that is. We'll show I will show you guys a diagram that shows you that these angles actually add up to the 360. The proof gets a little complex, but we'll show it to you so that it makes sense. So like you guys leave this class today knowing that the sum of the exterior angles of a polygon is 360 degrees. Even if you're not convinced now, we will show you. Okay, Before we do that, though, I do want to talk about a couple of things, and then we'll kind of get to this very nice visualization. So for regular polygons in particular, each exterior angle is actually going to be 360 degrees divided by the number of sides. So if we look at this square, we have four sides, right? And so if we do 360 divided by 4, we'll see that each exterior angle is actually 90 degrees. Okay, that like totally matches up. That's totally cool. Now, if we go to this pentagon over here, there's five sides, right? So 360 divided by 5 gives us 72 degrees for each angle. Okay, and I think that's why Enrica kept saying 72. She was talking about what the measure of these exterior angles were. Um, and because we know an exterior angle and we know that the interior angle is going to be supplementary, that means we can find the interior angle is 180 minus 72, which is 108. Okay, so that's really cool. We know that the interior angle of a regular polygon, a regular pentagon, is 108 degrees. Notice this only works for regular shapes, only regular polygons. If I had like some wacky pentagon that was like, I don't know, built like this regular, like this formula is not going to work with the exterior angles. They have to be regular polygons. That's super duper important. Cyprian says, so if you have six sides, you split 360 into six. Yeah. So if you have six sides, we can go ahead and draw a really quick hexagon. Wait, not this ugly green color anymore. Let's do this dark blue, right? Okay. So if I go ahead and draw oh, bad hexagon. Okay. You'll notice my drawing skills like low-key suck. Hold on. Uh, Okay, okay, yay, yay, beautiful hexagon. Whoopee. Okay, if we go ahead and draw out let's use a bright red. No, actually bright orange. I'm also really indecisive. We'll go ahead and draw all the exterior angles. Okay, so if we go ahead and divide all of these by 6, you'll notice that these are going to be 60 degrees, every single one of them, because this is a regular hexagon. So we can say that these are all equal. Now, because this is 60 degrees and these two angles are going to be supplementary, we can say the interior angle is 120 degrees. All of the interior angles are 120 degrees in this regular hexagon. This is like super duper important. Okay, how do we feel about that? Like, how do we feel about using exterior angles to find these interior angles? Like, is this something we're comfortable with? Do we feel okay with this? Okay, because this is like super duper important. And the fact that like we're able to figure out interior angles this quickly is like really nice because this is not always true in all shapes. But a really big thing that I want to emphasize is this only works for regular polygons. Only for regular polygons. If you have some funky shape like that little house figure I drew, you cannot use this. You have to find another way to get those angles. Okay, great. It looks like this is making a lot of sense to everyone. So let's go ahead and move on. Okay, really big thing that I want to emphasize again is, oh, Nahal asks, how can we find the angles in weird shapes? Honestly, I can't give you a good answer to that because the best way is literally to measure it with a protractor. Because otherwise, like you can't really tell aside from that if you use a protractor, or you can use a little bit of trig, but aside from that, there's not really a good way. Okay. Cool. Do you guys want to do like one more example with finding this, or do you guys want to go ahead? Okay, one more example. Cool. We'll do one quick example, and then we'll talk about like this like witchery with the exterior angle summing to 360 degrees. Okay, let's clean this up. I feel like this is just total chaos, and my colors like are so boring today. I feel like I really need to liven it up. Let's make it more exciting. Oh no, it'll totally ruin that. Okay. Trying to get everything in one go. Yeah. Yeah. All right, let's do, okay, one more. Okay, awesome, awesome. Can you guys pick a shape? Pick any shape. Let's not do any shape above 20 sides. And let's try not to pick a prime number either. Pick a shape and we'll go ahead. I won't be able to draw it. I give you no guarantees. Okay, I saw dodecagon first, and I like this one. This one's good. Okay. Go ahead and tell me what the exterior angle is in a dodecagon. And while you're doing that, I'm gonna take a crack at drawing a dodecagon. Or I might just give up. Oh, sky blue the color. Yes, I can do sky blue for sure. Okay. How many sides does this have? 12, right? I need to be really strategic in how I do this. 3, 4, 5, 6, 7, Oh man, I messed up. 8, 9, 10, 11, 12. Yes. Okay, I drew a dodecagon. You can see it really looks like a circle, right? Like you can't even tell if there's sides. Maybe I'll try to put some points. Um, but this is something that's like really cool, right? As you add more sides, your thing starts looking a lot like a circle. And that's not a coincidence, right? Because oh, you know what? You know what? We will talk about this in a second. We will talk about this in a second. Let's focus on the dodecagon because this is like a really cool thing. Okay. Cool. So this is a regular dodecagon. That's the intention. And everyone has answered. It's 30 degrees. That's absolutely right. Okay, pretty easy, right? We know that the exterior angle is just the number of sides divided by the number or the total number of degrees in a circle, which is 360, divided by the number of sides. So if I have 12 sides, 360 degrees, this is 30. Pretty easy. Now, can you guys tell me what the interior angle is? What is the interior angle? Amika, double check your math. I think you did it. Wait, am I tripping? Hold on. Maybe I'm tripping. Okay, yeah. Okay, cool. I'm not tripping. Okay, cool. Yeah. It's 150. For some reason, I'm seeing a lot of 160s. Okay, be wary. Maybe this is just a bunch of typos. Yeah. So the answer is 150. And the reason why that is because if we look here, we can, okay, this is probably not like the best side to pick because it's like really small. I'll do this side. Okay, this is 30. And if we look here, this interior angle is going to be supplementary with this 30 degrees. So if it's supplementary, that means it adds up to 180. So that means this is going to be 150. Okay, what do we think of this? Is this good? Are you guys comfortable with this? Good. Okay, awesome. So I think the idea itself, like applying these formulas isn't hard, but I feel like a lot of you still don't trust me. Like, okay, why is the sum of the exterior angles 360? So let's go ahead and actually talk about that now. So I'm going to briefly stop sharing my screen and I'm going to pull something up and then I will start sharing my screen again. Okay. Screen share. Cool. Wait. Um, all right. Are you guys able to see this? Is this like visible? Yes. Okay, lovely. Let me make sure a couple of settings are good to go. Cool. Ooh, how do I annotate? Okay, I want to annotate. Okay, cool. So let's start with this triangle, right? Let's go back. All right, so let's first start with interior angles, right? Interior angles, I feel like this is pretty easy. This kind of just goes to 180. This is not what I want to focus on. I want to focus on exterior angles. Okay, so what I'm gonna do is so you guys can see like there's some exterior angles, okay? So what I'm gonna do is I'm gonna slide this slider. And actually, can I make this bigger? Oh, beautiful. Okay, this is like gigantic. This is easy to see now. Okay, so what I'm gonna do is I'm gonna slide the slider and notice what happens to these angles, okay? Can I make this bigger? Okay. Sorry, I'm trying to make this like as easy to see for you guys as possible. Great. So what I'm gonna do, just gonna slide these together. Nothing is changing. All I'm doing is moving the angles. Okay, I'm moving the angles. Okay, and they come together perfectly. Okay, so now you might be like, oh, you guys don't see a shape. Oh no. Wait, did my screen just like disappear? Hold on. Does anyone see a triangle with like a blue background? No, you guys don't see anything? Oh no, this is so unfortunate. Okay, wait, let's see if we can fix this. Oh, my bad, you guys. Okay, can we see this now? You guys see a table. Oh. Do you guys see the Oh, okay, yes. Wait, I totally spoiled it. Okay, wait. Oh man. Okay. Let's go ahead and redo this. Okay, pretend you just didn't hear anything. You're gonna see this for the first time ever. So we are looking at the exterior angles here, okay? And all I'm gonna do, I'm gonna slide the slider and notice how nothing changes. None of the angles are changing. All I'm doing is just moving them closer and closer and closer, and they fit together perfectly. Okay, isn't that really beautiful? That's really neat. But some of you guys might be like, oh, this is a coincidence. This triangle is just specific. It just happens for this one triangle only. Okay, well, this isn't a cute triangle, so let's go ahead and make it obtuse. Okay, let's make an obtuse triangle. Like a super obtuse triangle. Okay? And now we're gonna do it again. The angles are not changing. I'm just sliding them together. Just pushing them together. Okay, and they line up again. And this is scalene. This is an obtuse triangle. This is like the least coincidental triangle ever. But if you still don't believe me, I can do it once more. Let's choose another wacky shape. Let's do like this thing. Okay, I feel like this is a good shape. Okay, I'm just gonna oh wait, this is like not a great shape. I lied. Okay, I don't want this to be like too big. Slide it up, slide it up, slide it up. And it fits together beautifully. Okay, so this is like an idea of how this like works. Obviously, this is not a proof, but to convince you guys that this actually works, I wanted to show this. Maybe you're just like, okay, this only works for triangles. Maybe you're a true skeptic and you still don't believe me. So we're gonna go ahead and look at another shape. Let's look at quadrilaterals instead. Okay, let's look at quadrilaterals. I'm gonna ace the screen sharing this time. Like it's gonna happen. Okay, there we go. All right, so I've got interior angles, which I don't really want to talk about. Let's talk about exterior angles, okay? So I'm gonna go ahead and let's make this a little smaller. Okay, so we got a pretty wacky quadrilateral here. I'm gonna go ahead and slide this. Slide. Okay, so one angle is in place. That's not a circle yet. So let's go ahead and put that other angle in place. Notice how all I'm doing is I'm sliding along one line. Like I'm not changing anything. I'm just sliding along one line. Okay, and now I'm gonna put that next angle in there. Notice how it's staying just along that side. It's not moving, it's not changing or anything, and it fits in perfectly. Okay? Fits in absolutely perfectly. Yeah, this circle is split into four parts. They're not equal parts, but they all correspond to exterior angles. Okay, maybe you're a true skeptic and you're still like, okay, that was just a weird quadrilateral. So let's look at this instead. But notice how even when I change this side, it still stays a perfect quadrilateral. I can go back, put this back, and it's perfect. It matches up exactly with those other sides. So maybe you're like, okay, it's just triangles and quadrilaterals. I mean, those shapes have a lot of special properties. Well, we can show it too with hexagons. Let's look at a hexagon. This will be our last one, but I really want to convince you guys, like this is a legit thing. Oh, wait, maybe if I can get it to work. Ooh. Oh, okay, hold on. Technical difficulties. This is like super anticlimactic somehow. Okay, well, maybe not a hexagon. Let's do a pentagon instead. Yeah, this is like super satisfying. I think it's so cool to see how it just like lines up perfectly. Okay, this is like kind of regular, not really, but wow, look at that. Look at how that fits together. Isn't that beautiful? Let's maybe do like something wacky. No, I don't want to do reflex. Okay, this is a pretty wacky thing, and it still fits together. Okay, I do see some. Oh, yeah, yeah. Someone is asking about a pentagon. Here's your pentagon. I do see a couple of questions. Oh, Nahal asked, what would happen if you turn the quadrilateral into a triangle? Okay, if you turn the quadrilateral into a triangle, because you're reducing the number of sides, your total sum of the angles inside the triangle is going to decrease, but the exterior still stays the same. Notice how even as we added more sides, the sum of the exterior angles didn't change. It's always been like a circle. That's really neat. So I guess something that maybe some of you guys are noticing is that all of these angles that I've had so far are less than 180 degrees. So let's do something crazy, right? Let's put one angle like inside. Okay, so that way this entire angle is now going to be greater than 180 degrees, but still less than 360, okay? So this is the reflex angle we're talking about. Are you guys like okay with this? Is this like mind-boggling yet? Yeah, so some people are saying, yeah, there's starting to be some overlap. Okay, so let's go ahead and connect these. Obviously, you guys can see like this is probably not going to be exactly 360 degrees because this reflex angle itself is kind of whack. Yes, I will send you guys the link. It'll be in the handout. But anyways, if we connect this together, then our really, really perfect 360-degree triangle or 360-degree circle gets messed up. We can't say exactly how big this is, but we know for sure it's greater than 360 degrees, like Cypernith says. So that's something really important about this property that we're discussing. So the sum of the exterior angles is only 360 degrees when we're dealing with convex polygons. So this idea of convex basically means that the angles are all like pointing like outside. Like you don't have, hold on. I think this is a moment where I have to go back to my whiteboard. So let's stop sharing. Oh, how do I get out of here? Okay, cool. And let's go back to the whiteboard. Okay, awesome. So convex looks a little something like this. Basically, the angles are pointed like outwards, right? So I have the rest of my sheet, and then like the angle is going away from the center of the polygon. So this is convex. Now, the opposite of this is what we call concave. So this is something that's like going towards the center of the polygon. This is concave. And when we have a concave angle, this angle is going to be greater than 300 or greater than 180 degrees. That's why it kind of messes up with all these nice polygon things we're talking about. All the polygon properties we're talking about apply only to convex. The nice thing is that a lot of math problems only really care about convex like polygons. You don't really see a lot of stuff involving concave just because they get so messy for everyone. So this is like this is a good distinction to know, but like, don't worry if you're like, oh no, I don't know how to deal with concave. That's okay. You probably won't have to for a good bit of time. Convex is what's important. Is this idea okay? I know this is like pretty brief, so if you guys want me to go a little more in depth, I can. But if we kind of get the idea, the gist of it. Okay, I don't see any questions. If you guys do have questions and you're just afraid to ask in front of everyone, you can DM and we'll talk. Okay. Cool. Okay, no questions. So I think let's go back to this idea. Okay, so I know before, like, I was going on a little bit of a tangent, right, with this dodecagon thing. I was like, guys, doesn't this look like a circle? And then I started like rambling about something. So let's return to that conversation. Um, does this look like a circle? Let's start there. Does this look like a circle? This dodecagon. And you know what? Let's clear the board because I feel like this is a pretty important discussion. We need to talk about whether or not this dodecagon looks like a circle. Okay, yeah, it kind of does look like a circle. And maybe I'm not the greatest drawer, right? Like maybe my drawing skills just suck and like, I don't know, like this is just a bad dodecagon. Okay, so let's go ahead and get a picture of like a legit geometric dodecagon that some professional has drawn. Let's Google one really quick. Dodecagon. I don't know if you guys can see me Googling, but that's okay if you can. Okay, here's a nice dodecagon. I'll get a blue one. I'm gonna copy this and I'm gonna put it. Oh, you guys can just see all the tabs I'm going through. Amazing. Okay, here's our dodecagon. And I'll get rid of this ugly thing down here. Nobody wants to see this. Okay, beautiful. Okay, so this kind of looks like a circle. Maybe you can still see like, oh, I see some sides. This is cool. All right, let's go to something that has 20 sides. I don't know what this is called. I think it's like icosode. I don't know. 20 side polygon. Polygon. What is that? Okay, this is gonna be this thing. It's an icosagon. Okay, I had the right instinct. Let's get this yellow thingy. Copy image. Okay, I'm gonna close this. All right, so this is gonna be our 20-sided polygon. Does this 20-sided thing look a little bit more like a circle than this dodecagon? What do you guys think? Yeah, it does. Okay, and I do see some interesting ideas about like why this might be. Yes, we will absolutely come back to that. So, Sean, good idea in the chat. I like where you're headed. Um, yeah, so this really does look like a circle. And the more sides I add, the more and more it looks like a circle, right? Because to fit all of these points, my sides have to get like super duper small, like really, 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 really small. Okay, so the more points I add, the more smaller my sides are gonna get. What do you guys think about these angles? Do you guys think these angles are getting bigger and bigger? Yeah, it looks like these angles are getting bigger. We know in a dodecagon, the interior angle is going to be 150 degrees. That's pretty easy. Can you guys go ahead and calculate what the interior angle of this 20-sided polygon is? What is this interior angle? Oopsies. Oh, just the interior angle, not the sum of all the angles. Sorry, I should have clarified. Yeah, it should just be 162. So it's not like much bigger than 150, but it's certainly bigger, right? And it's certainly getting closer to the 180 degree mark. Okay, this is pretty interesting. This is pretty interesting. And obviously the exterior angle is also getting like super small, right? This is like 18 degrees. Man, that is tiny. Okay, so someone said let's do something with 100 sides. Let's look at 100 sides. I don't know if this exists. Maybe it does. We'll see. Okay. Man, this is like kind of crazy. Yeah. Okay, I see someone has put a picture in chat. Let's see if I can get one with some colors on it. Um, I don't know. Okay, you know what? It's fine. We'll do something light. I don't think this will show up though. Okay. Here we go. I'll color it if I can see. Okay. So this is gonna be something with 100 sides. Okay. That totally looks like a circle. Would you believe me if I said this was not a circle? What do you guys think? Would you believe me? No, right? Because like all these sides are so tiny, like it doesn't even look like a side. Unless I zoom in like 10,000 times, I really can't tell a side from a side, right? So this really does look like a circle. So this is like a really interesting idea. The more sides, the more points we add, the more it looks like a circle. Yeah, and Cypress says if there weren't even those dots, it totally wouldn't look like a circle. Oh, and Vika did a really nice job for us calculating the interior angles. That is 176.4 degrees. That is like ridiculously close to a line, right? That's like super duper close to a line. And this goes to show like the more points you add, the more and more and more it looks like a circle until we add an infinite number of points. There's no more points to be added because they're all on this circle. So I know everyone says like a circle is something without any sides. It's got no vertices. Well, another way to think about a circle is that it has an infinite number of sides and an infinite number of vertices. What do you guys think about that? Is this like mind blowing? Like, what do you guys think? I think we're just like all like, wow, jaw drop. Like this is pretty cool, I think. I think this is pretty neat. That's why I got a little excited before. But I wanted to take a moment and like break this down. Oh, this is a hectagon. Hecta I don't hectagon. Okay, yeah, never mind. This is a hectagon and this is an Isogon. Cool. So basically, this is a pretty cool idea. The next time someone says like, "Oh yeah, a circle has 0 sides," you could be like, "No, a circle has an infinite number of sides." And this actually like this idea that you can add a bunch of like points and add more vertices and make it closer and closer to a circle. First of all, this kind of touches on a little bit of calculus, something that we call a limit. That's totally beyond the scope of this, but this is like super cool. But then also notice how when you get to a circle, right? The sum of all the interior angles is 360 degrees. And that's kind of the motivation for why the sum of all the exterior angles in any other polygon is also 360 degrees, because they all kind of make up this circle. So that's like kind of the analogy here. But then on the other hand, we also see that the exterior angle, well, it's going to be 0. There is no exterior angle. So that's like a pretty cool thing. There's a lot of like paradoxes with circles. So I thought that was like a cool way to re-describe circles. Okay, what do we think? Yes, this is cool. Okay, I'm glad. I'm glad you guys think that. Maybe this is if this has not been interesting to you, maybe this is just like, oh, this is totally like hypothetical. I don't believe any of this. Okay, that's okay. We'll transition for now. If you're totally fascinated about this and want to talk more, we can talk more. What's a paradox? A good question. A paradox is something that is both true and false at the same time. There's some good paradoxes out there. I can't think of any off the top of my head right now, but a good one that we're just talking about now is the fact that a circle has both 0 sides and 1 side, or 0 sides and an infinite number of sides. Yeah, there you go. That's a paradox. Okay. Yeah. Yeah. Yes, yes. Oh, what's the coin flipping paradox? I'm not sure. Okay, anyways, we'll talk about paradoxes later. Let's return to our discussion of polygons, right? So I think some of you guys accidentally saw this before. You got some behind the scenes look of how I run this class. Here's the table. Here's a table that you guys probably accidentally saw before. Um, but yeah, so this is just a quick like reference sheet for like polygons, the sum of their interior angles, exterior angles, etc. Honestly, I would tell you guys do not memorize this, because a lot of this is like very easy to remember just like intuitively, right? We know very quickly how to calculate exterior angles. And honestly, that's the only thing you have to remember because once you figure out an exterior angle, it's pretty easy to figure out the interior angle from there, and then the sum of the interior angles. So don't memorize like row by row. Honestly, just understand how to calculate an exterior angle, and you'll be able to understand the rest really easily. Okay, what do we think? Is this good, you guys? Okay, I don't see any questions. We have 5 more minutes left, so let's go ahead and just end with some practice problems, and then we'll conclude today's class. Okay, cool. Um, okay, I know I said we get to triangles today, but I think I just like I was so excited about polygons that I just talked about polygons the entire class. But that's okay. I think it's important that we talk about these things in depth. All right, so pretty easy question. Calculate the sum of the interior angles. Angles in a decagon. Decagon. So that's going to be 10 sides. Okay, yeah. So I do see some different answers, but they're all like related to the thing. So this is where these angle problems can get a little tricky. Make sure you understand what the question is asking, right? So we're trying to find the sum of interior angles. So we can find the exterior angle pretty quickly, right? We know that the exterior angle is going to be 360 divided by 10. So the exterior angle is 36 degrees. This is exterior. So that means the interior is just going to be 180 because this is supplementary. The exterior and interior are supplementary. It's going to be 180 minus 36 or 144 degrees. Now you can find the interior angles, the sum of the interior angles pretty quickly from here. If all of the interior angles are 144 degrees and there's 10 of them in a decagon, that's going to be 144 times 10, which is 1440, and that is our final answer. Or you could do the way with the triangles. So you find that there's 10 minus 2 triangles, and then multiply that by 180. So that's also 1440 ways. Okay, pretty easy, pretty simple. This is good. All of you guys like had something on the right path. I just think you guys didn't read the entire question. So that's where we kind of went wrong. So yeah, just make sure we're aware of that. Okay, lovely. Let's do one last question and then we'll go ahead and end for today. Um, let's see. Okay, we'll find out like how many sides a regular polygon has. Okay, let's clean up all of this. Okay. All right, our final question for today is actually going to be two parts. Two parts. Okay, go ahead and answer part A first, and then we'll go talk about part B. All right, so we have an exterior angle of 24 degrees, and we want to figure out how many sides does this polygon have? Okay, I see an answer from Sai Praneeth of 15, and Shanik also says 15. Let's see if some other people agree. Ratika, Amari all say 15. Atharv says 15. Awesome. Rohan says 15. Okay, cool. So I feel like 15 is kind of the right answer here. And thankfully, this is not a trick question, so you guys all got this right. Good job. So the way we find this out is if the exterior angle is 340 degrees, remember, we know that 360, or sorry, 24 degrees. I don't know why I said 340. Okay, we know the sum of all the exterior angles is 360, right? And we know that 360 divided by the number of sides, n, is going to be equal to the exterior angle, which in this case is 24. So this is a pretty simple algebra equation, which you guys are pros at. So if I go ahead and solve, I'll find that n is equal to 360 divided by 24, or 15 sides. Okay, so 15, pretty easy. Can you guys find the interior angle now? This is probably easier than the previous part. Yeah, it's just 156, right? Because we know the interior and exterior angles are supplementary. Really key point. So if they're supplementary, I can subtract 180 minus 24, get 156 for the interior. Okay, and that concludes this problem and today's class. You guys have done a really wonderful job. I hope you learned something new. I hope you found like our discussion exciting, even if it was definitely a little slower than normal. I hope this was like inciting. If you guys think that there is something that you really, really want to cover, definitely suggest a topic and we'll talk about it at some point in the class. We'd love to hear what you guys want to learn so that you can get the most value out of this class. So if there's anything like you're really curious about, anything you struggled with historically, let us know and we'll try to incorporate it. Next week, we'll narrow our discussion specifically to triangles. Okay, awesome. Thank you guys so much. You are so free to leave. I loved having you all tonight. I hope you had an equally great time, and I will see you all next week. Bye, everyone. Yeah, thank you guys all. Yeah, bye, everyone. Thanks, you guys. Bye, Mari. Bye, Thor. See you next week. And Vika, I do see your question. Okay, is there a competition math course? I would say I feel like both our algebra course and our geometry course kind of gets into competition math. I know this is a little um, early on that side. If you're looking for more like middle school stuff, that'll probably come uh, towards the end of this month and early October. We'll kind of start covering more of those advanced topics. I wouldn't say we have like a specific prep. We're not running like a specific prep class as of now. That might be something we look forward to maybe in like October as the competition season comes up. But yeah, if you're interested in that, we will definitely see if we can add that one. Yeah, of course. Thank you so much. Okay, for those of you all that are still here, if you have questions, please let me know. Otherwise, I will go ahead and close the meeting. Okay, I don't see any other questions. If anything comes up, feel free to email me. Bye, everyone.